Now if you assume the gain, your gain of first stage, let us say assume 40 dB and second stage maybe 20 dB or so. So, with the 60 dB if you start, and this is your first pole, low frequency pole, what was that frequency? 300 kiloradian. So, 300 kiloradian if you start and 60 dB is the DC gain. So, 3 decade. So, 300 K into 1000. So, UGB will fall at 300 megaradian per second. So, both the other poles are outside your UGB. So, you may not need to compensate with this spec, but you know that let us say you put a microfarad cap, then what would happen? So, omega P3 is outside your UGB. So, assume C out equal to, instead of 10, let us say I assume 10 microfarad, which is 10 to the power 6 times what you assumed earlier. So, your omega P3 will come at 1.67 kiloradian. So, this will become now dominant pole, and now if you again start with the same 60 dB, so your UGB will fall at 1.67 mega. So, again you do not need a compensation. So, which means if you use a very large C out or very small C out, in both the cases you may not require a compensation because it will behave like a first order system. But now if I assume a nanofarad, let us say 10 nanofarad, so where will it fall?
UGB will fall at 1.667 gigas.
Not giga, I am asking what will be the omega P3 for. So, assume C out equal to 10 nanofarad. So, omega P3 will be 1000 times of this, 167 kiloradian. And where was your omega P2? 300 kiloradian. Okay. So, now both are pretty close to each other. Now, you have a second order system which needs to be compensated. Okay. So, you need to consider the case of C out. If you are designing for a very low C out cap, then in that case, for this particular load current you may not have to compensate, but the problem here is your load can be 0 also, you do not know. Okay. So, both the cases you have to consider. There could be a case where your system is drawing a fixed load, let us say it is an on off system, which means it is either drawing a no load which is turning off. In that case, if it is turned off, you do not need to regulate the supply at all. In that case, you do not need to bother. When the system is turning on, it will only draw let us say 10 milliamp current. So, in that case, you have to look at what your basically whether you require a compensation or not, it will be determined by the C out. But if your load is variable, let us say 0 load to 10 milliamp. So, at 0 load what would happen? Hypothetically, when I say 0 load, R load will become infinite. So, the current which will flow into this will be only the feedback resistor. You have another R on which I am not showing here, the beta factor, and that is usually very large. I mean that both the resistance may be like of 100K minimum value, sometimes they are mega ohm also. So, even if you choose 100K, 50K each, they are in series. So, and it is a 1.5 volt. So, 15 microamp current. Now, at 15 microamp, you have to determine what will be the R out. R out will be very small, very large here. So, even with a 10 picofarad, you might see your pole might fall within your UGB and you may have to compensate at light load. And since we are designing the LDO to cater to all the load variations from 0 to up to 10 milliamp. So, we have to consider the worst case. So, the worst case here will be the 0 load current. So, if you compensate it for 0 load current, it will be automatically compensate for higher current, because at higher current you know the output pole will be moving further at higher frequency. And if you are not, if you are designing for a fixed load, then what will be the worst case? Worst case will be the mid range cap order of nanofarad, where your two poles, both the poles, basically the omega P2 which is the fixed pole and the variable pole which is the output pole, which is depending on the output cap, both falls within your UGB. So, that is why there is not a fixed, basically you cannot consider a fixed cap and fixed load and design it, because it may become unstable in a. So, you have to always consider the worst case, and worst case will always be defined by when both the poles, the omega P2 and omega 3 falls within your UGB. And mostly when they are falling within UGB, the worst ever case will be when both are very close to each other. Okay. So, most of the time when we are designing a capless LDO, there is something called capless LDO or capacitorless LDO, where on the output we do not put intentionally any cap, it is only parasitic caps and order of picofarad. In that case, you have to design for a or compensate it for the lightest load, which is your order of microamps. Okay. So, if I have to design for this 10 nanofarad case and 10 milliamp, how are we going to compensate? How can you compensate this? No, C out is fixed, 10 nanofarad. Then you do not have any choice. You have only choice to put the capacitor at omega P2. I mean, you are designing for. So, if you already had a very high cap, then it is self compensated. When I choose C out of 10 microfarad, what does it mean? It is a self compensated, because second pole is outside UGB. You require a compensation only when your C out is falling within range of 10 nanofarad or so. You know you require a compensation, and the only choice now you have to add the cap at omega P2. So, for this particular case, so let us first draw the. So, let us say 60 dB your gain. So, this is your omega P3, because this is falling at lower frequency 167 kiloradian per second, and then so it will drop with minus 40 dB per decade. So, where will be your UGB? Where will your UGB? At what frequency? 3000 what?
3000 because per decade 60 minus 20, so it will be 40. 40 to 0 is already.
No, you have to drop by almost pretty close to 60 dB, you can say, because these poles are very close. So, you might be losing maybe 10 dB here also, not more than that at this point. So, you have to now cross 50 dB more. So, 1 decay. So, at 3000 kilohertz, 3000 kilo or 3 mega radian, you will drop by minus 40 dB only. Okay. So, you still have almost 10 dB more to go with, and in order to go for 10 dB, how much you require? 3 times or what? It's 20 log 10, huh? 20. Yeah, roughly 3 times, huh? So 3 mega into 3, 9 meg. So if this is 0 dB, and what about the phase? What will the phase at 0 dB? Almost 180, phase shift, because both pole will have 90-degree phase shift. So phase margin is 0. So phase margin is 0, which implies unstable. So if I want to push this omega P3 outside your UGB, which means omega P2 now have to be reduced. And what will be the UGB? How will you decide the UGB? So you remember, for 60 degree, let's say I want a 60-degree phase margin. So your second pole should be, or the non-dominant pole should be, roughly 1.7 times of your UGB. So omega P3 is now fixed, we cannot change that, which means your UGB should be 1.7 times less than omega P3. Compensated, I am calling it, so don't get confused, should be okay, let me first call omega UGB should be okay, and omega P2 compensated should be what frequency? Omega UGB over, sorry, omega UGB, yeah, divided by your gain. dB, which means omega P3 is known 300, sorry, 170, 167, yeah. So 167 K divided by 1.7, how much is this? $98, so pretty close to 100. And omega P2 compensated should be divided by 1000, correct? Now you calculate the cap value from there. So, R out was known for omega p 2, $500K. So, omega p 2 is 1 over 500K multiplied by, I will call it CC, compensated cap, plus CO2. So, now you are adding another cap in parallel with this. So, you have to find the total cap, required cap. This should be 100 radian per second, which means Cc plus CO2 equal to 1 over 5 into 10 power 5 into 100. So, this goes up, this will become 10 power minus 7 over 5. If I make it 100 over 5 into 10 power minus 9, this becomes 20 nanofarad. Okay. So, the total cap required is 20 nanofarad, and you know CO2 was like order of picofarads. So, it is very negligible. Even you subtract this, it does not matter here. So, which means the capacitor required is a off chip cap, you cannot even compensate with the on chip cap, correct. So, if we are compensating using the output pole, you may require order of microfarad cap, because your R out is very small there. So, your capacitor requirement will scale up, but if you compensate at omega p 2, then the capacitor requirement will be relatively lower compared to the output pole. Okay. So, that is why most of the time we, and in this particular case it is coming at order of nanofarad. I mean, with the Miller, let us say without Miller you might be getting 100 picofarad also, with Miller you might get 10 picofarad also. So, that is a difference, but even without Miller you can compensate it, because 100 picofarad is also possible to put on chip. The only thing is your area will be much larger, and that is why we go for Miller cap to reduce the area. So, we will take the case where your capacitor requirement will be order of maybe picofarads, hundreds of picofarad, or maybe maximum 1 nanofarad, and then we will see how can we reduce that cap with the Miller compensation. Okay. Then after that there are some more compensation techniques, we will talk about that as well. Okay.